All right, so today we're going to do a couple of application problems, doing the types of things we were doing last time with the systems of two equations with two unknowns. I should say linear systems of two equations with two unknowns. Then we'll get into doing systems with three equations and three unknowns and doing solving those types of systems as well. So, and we'll continue that next week as we're getting into Thanksgiving. So, anyway, any questions at all before we get started, though? All right. Well, let's look at these first couple of problems here. Mainly, it's about just getting the problem set up so that we can get a system and see what the system is, and then solve it just like we did last time, either using substitution or elimination. So in this one, we've got a boat traveling 20 miles upstream in 150 minutes, and then it travels downstream and it takes 60 minutes. So it wants to know what the speed of the boat is relative to the stream, and then what the speed of the current is. So what it means for that first part is what's the speed of the boat without if the stream were, if it were, say, on calm water, not going on a river or a stream or what have you. All right. So notice when it's going upstream, you're going to have, pardon me, you're going to have the current working against you, and when you're going downstream, of course, the current will be working with you. So let's say we let variables be a couple of these different things. Let's say x is the speed of the boat. And y is the speed of the current. Oh, by the way, I should have mentioned this before I started. Notice I've got actual number and page number on here. These are the numbers. These problems are in the book. So if you wanted to look at the book for reference for where these are in the book. That was why I put those numbers on there for you. All right. So let's think about how we might get the equations that we need in this case. Again, if you're looking at traveling upstream, the boat and the current should be going in opposite directions, right? Now, of course, a big principle that we're going to use here is that that distance equals rate times time principle, right? So what should happen when you are traveling upstream in this case? What do you think is going to be the relationship between your x and y if you're going upstream? What should you be doing with the x and y, I guess I should say. Are they working together or working against each other? Against each other. So what do you think you ought to do with the x and the y if they're working against each other? Remember, we're doing linear equations, right? What does it mean for an equation to be linear? Let's think about that. We're trying to create a linear equation. What has to be true about your variables in a linear equation? That has nothing to do with this problem. What does it mean to be a linear equation? What's true about the variables? Talked about this last time. What's greater than 1? Let me ask you this. If I put natural log of x in an equation, is it linear? Or if I do e to the x, is it linear? No, what's wrong with that? What's that?
It's not a straight line.
It's not a straight line. Okay, so what's true about the variables if you talk about an equation of a line? What's true about the variables? So, what do you mean by that?
Like it's consistently going up at a rate, the same rate.
Okay, so you're thinking about the slope, is that what you're thinking? Okay. So, true, we always have a constant slope, that's true. But what about the actual variables? The variables are to the first power, right? Can you divide by a variable? No. Can you do log of a variable? No. Can you do a square root of a variable? No. It has to be variables to the first power. Can you multiply x and y together? No. When you see the variable, it literally has to be all by itself to the first power. So let me ask again. Going upstream, are we helping or hurting? Is the current helping or hurting going upstream? Hurting. Now, again, you're trying to create an equation. If everything has to be the first power, and you want the current of the speed of the current to hurt the speed of the boat, what do you think you should do with those variables? Subtract them, right, good. Yeah, we should have an x minus a y, right? That should be representing your speed upstream, right? Your boat's going upstream, the current's working against it. That should be your speed upstream, right? Overall, how fast is the boat going upstream? It says it goes 150 or 20 miles in 150 minutes. So what would be the speed going upstream then if you go 20 miles in 150 minutes? Because I have to have this equal to something, right? I have to set an equation. What do you usually measure speed in? Or what? Give me some units that you measure. Yeah, distance divided by time, right? So 7.5. Wait, what did you do for 7.5?
Divided.
Okay.
Would that be?
So that's going to be minutes, but that's time divided by distance, right? So it's upside down. So I should do the 20 divided by the 150 if you do miles per minute, right? That would be in miles per minute in that case. You could also do miles per hour. If you want to do miles per hour instead, what would you divide by instead of 150 minutes? How many hours is 150 minutes? 2.5, right? So if you want to do miles per hour instead, it doesn't matter as long as you're consistent, right? This is a speed, correct? So the x minus y is representing the speed upstream. You go 20 miles in 150 minutes, so you should set that equal to 20 over 150. What should the other equation be then? When you're going downstream. In this case, is a current helping or hurting? Helping. So how would you represent helping as opposed to hurting? X plus y, good. And what should that equal? Where did the 20 over 150 come from? Yeah, so it should be 20 over 60. Good. All right. Again, it's still distance over time. Or again, if you wanted miles per hour, you do 20 divided by 1. It doesn't matter as long as you're consistent in each equation. So now we have our system that we can solve. And at this point, we should be able to solve it using either elimination or substitution, whichever one you would prefer. I prefer elimination in this case because what would I need to do with those two equations to eliminate the y? Just add them, right? Because the y's already have opposite signs, correct? Yep. All right. So when we add, you'd have 2x. Add those together. You have 2x. The y's cancel. Let's see. That first fraction reduces to 2 over 15. And the second one reduces to 1/3. 1/3 is the same thing as 5 over 15. So it looks like we get 7 over 15. Might have been a little bit nicer if we had converted it to miles per hour, but that's okay. Divide by 2, we get our x is 7 over 30. Again, the units for this, since we did 20 divided by 150, that's miles per minute. We did 20 divided by 60, that's also miles per minute. This should be miles per minute. If you wanted to convert it to miles per hour, just need to multiply by 60 and you get 14 in that case. Now that I figured out the x, how can we figure out the y? Yeah, plug the x into either one of these equations and figure out the y, right? Doesn't matter which one. You should get the same answer both times. I'll plug it into the second one. So 7 over 30 plus y equals 1/3. Subtract your 7 over 30 over. I should get 1/10. Because I get 10 over 30. When I get a common denominator out of 10 over 30 minus 7 over 30 gives you 3 over 30, so you'll get 1/10. Again, that's miles per minute. If you again wanted to convert that to miles per hour, you could multiply by 60 and you would get 6 miles per hour. But again, notice that the process for solving the system is exactly the same like we talked about last time. We just got to get the equations set up, which took a little bit of effort this time. Right. What questions do you have about that one? Right. Well, let's talk about the next one. You've got a gas station that charges $3.60 a gallon for regular gas and $4 a gallon for premium gas. They tell you that they sold 185 total gallons and made $690 from selling the gas, and wants to know how many gallons of each type were sold. So again, the first thing we want to do is get a system of equations set up, because again, once we get an system set up, we can solve the system just like we solve every other system that we've talked about. If we're going to get a system set up, we probably should identify some variables. It says how many gallons of each type were sold. So how many variables are we going to need in this case? Two. Good, because we're looking for a number of regular gallons of gas and number of premium gallons of gas. So we'll need two variables in this case. So it doesn't matter what you call the variables. I'll call them x and y again. So let x be the gallons of regular gas and y be the gallons of premium gas. Oops. So again, we have two variables. Anytime we try to solve a linear system and we want to find exactly one solution, we better have as many equations as we have unknowns. We're looking for two variables, so we better get two equations. So there better be enough information in the problem to give us two equations, to get two equations out of it. What's one equation? What's one piece of information you think you might want to use? Okay, so price per gallon is probably going to be helpful for one part of that. So what equation can we get if we use the price per gallon pieces? Say it again.
3x plus 4y.
And what would that equal?
That would equal the total of 690.
690. Okay, so good. So notice that we have $3.60 per gallon. So instead of 3x, it should be 3.6x. Good. So good. So the total price for the regular gas would be 3.6 times x, right? That would give you the amount of money you made from selling regular gas. And 4y would be the amount of money you made for the premium gas. And all together, that better be $690. That's one equation. And that's basically a total revenue equation, if you will. What's another equation? Okay, so we need to set it equal to 185, but what do we need to set equal to 185? I agree that something needs to be equal to 185. It says that's the total number of gallons. Say it again? X.
Or is it x plus y?
And why would it be x plus y?
Because that's the gallons.
Good. Yeah, so it says they sold 185 total gallons, right? So x is representing gallons and y is representing gallons. X plus y will represent the total number of gallons. So the first equation we have is x plus y equals 185. The second one is 3.6x plus 4y equals 690. Now we have two equations and two unknowns, so now we can solve it. Again, we can use substitution or elimination. Which would you prefer to use in this case? Okay, you can do substitution. Okay, so if you're going to use substitution, what do you need to do? That's the other one.
Oh, well, I was thinking of
You want to do the elimination instead? Okay. So what do you want to do elimination then? Okay. Multiply the top by -4. Get -4x minus 4y equals, what is that? Negative 740. Did I do that right? Okay, good. So remember again, if you're using elimination, you want to match up the coefficients to be the exact opposite for one of your variables, so that when you add, it goes away. Okay. You could either multiply by -3.6 or multiply by -4. Doesn't matter which, they decided to get rid of the y, which is perfectly fine. You also got rid of the x first. We need to now do what with these two equations? Add them together. So let's add down. We get -0.4x. The y's cancel, equals what? -50. So now divide both sides by -0.4 equals 125. Good. We got 125 gallons of regular. How do we figure out how many gallons of y will there be? Either of them. Yeah, good. You can plug it back into either of them. You should get the same answer. As a matter of fact, it's a good check that you've got the right x value. Okay. You should be able to plug it into both equations and get the same value for y. It's easier to plug it into the first one. You should get 60 for y. That okay? Any questions on that one? All right. I want to leave the last one for you for practice because the last one should look a lot like that previous one. Okay? So it'll be a good practice one to do. All right. So let's go on So all we're doing in the next section is bumping this up a little bit. Instead of going to do systems of equations with 2 variables and 2 unknowns, we're going to bump up the number of unknowns. And basically, we'll probably do 3 and 3. But in general, we could extend this to any size that we wanted. So all we mean by a system in a linear equation in n variables is that it has the form we write it as a1x1 plus a2x2 plus anxn equals some constant. So the n variables that we have in this equation are just represented by x1, x2, x3, and so on up until xn. Again, notice that the fact that what makes this a linear equation, again, is the fact that each of the variables are only raised to the first power. You do not divide by a variable. You do not do the square root of a variable. You don't do e to a variable. Okay? When the variables appear, they only appear to the first power, so you don't square a variable either, any of those kinds of things. And you don't multiply the variables together. So the only thing that you can do to a variable is multiply it by a constant and add it to another term that looks like that. Okay? On the right-hand side, we have a constant as well. So the A1, A2, AN, B, all of those are constants. Okay? A1, A2, AN, and B are constants in this case. Okay? They're numbers. That's what makes it an equation linear. Okay? Basically, it's like the most basic type of equation that you can get. All right, so the next part here is just saying how many solutions does a system of linear equations and it possibly have? And I should have put the word linear in here because if it's not linear, what I'm going to say is not necessarily true. But we talked about this last time, right? When we did lines. What are the possible ways that you can draw your lines? Well, they could cross, right? You can get how many solutions if they cross? 1. They could be parallel, none, or they could be the same line, infinitely many, right? We also talked about, if you think about planes, like the floor and the ceiling and the walls, you can imagine no solution, you got parallel planes, right? You could get infinitely many solutions. If you have, say, 2 planes meet and you get a line, or you get exactly 1 solution, kind of like the corner of the ceiling and 2 walls, right? But that's it. That's all you get. Okay. So any system of linear equations, doesn't matter what the system is, any system of linear equations has no solution, exactly 1 solution, or infinitely many solutions. There are no other possibilities. All right. So just like what we talked about in systems of equations with 2 unknowns, we can solve the system of equations with 3 unknowns using substitution. Tends to get a little bit uglier, but we can do it. Okay? So if you're going to solve a system of equations by substitution, I've got to use one of the equations to solve for the variable and plug it into the other two to start with. Okay? So doesn't really matter which one you do. I would look, if you're going to do this with substitution, I would look for something that's easy to solve for. So for example, if I look at the first equation, I can solve that easily for x just by moving the other stuff to the other side, right? I can add the 3y and subtract the 2z over to solve for x. That's pretty easy to solve for x in that case, isn't it? So this first one we can write x equals 3y minus 2z plus 1. And now what we'll do with this expression is we'll take this expression for x and plug it into the other two equations. Okay? So we'll have 2 times 3y minus 2z minus y plus 2z equals 0. And, oops, I forgot my plus 1, didn't I? Sorry. And then do the same thing in the second equation and plug that in for x as well. So literally just took out the x and put in the expression for x that we just found. And what we've done, of course, is we now have a system of two equations with two unknowns to look at. At this point, we want to simplify. We would distribute the 2 through and then combine like terms. So you've got 6y minus y. So you'd have a 5y in that first equation. We've got a minus 4z plus a 2z. So we get a negative 4z, or negative 2z, sorry. Distribute your 2 through to there, we would get a 2, and I'll subtract it to the other side and get negative 2. So again, if you need to do it in steps, that's fine. All I did was distribute the 2 and combined like terms, and I moved the constant to the other side. In the second equation, what will we have? What's the y term going to be? 4y. The z term will be, negative 1z. Yep, good. And then I'll move the 1 to the other side, and we'll get 5. Can we do that? So we've taken the 3 equations with 3 unknowns and reduced it down to an equation, or system of equations with 2 equations with 2 unknowns. We can substitute again. Same concept, substitute again, and see if we can knock down another equation. Looking at those two, that system of equation, what equation and what variable might you want to use? Yeah, do the 2 and then solve for the z in the bottom one. Probably a little bit easier, right? So in the bottom one here, you'd have negative z equals negative 4y plus 5. And then multiply both sides by negative 1. And get z as 4y minus 5. I didn't have to divide by anything to solve for z in that one, right? If I'm doing substitution, probably a little bit easier to solve for a variable. You don't have to divide a constant and see if we get a whole bunch of fractions. If you can't always. But at least for computational purposes, it helps most times if you don't have to make fractions, right? So now what do we do with this? We use the second equation to solve for z. What should we do with that now? Into the, which one?
5y minus 2z.
Good. Yep, good. Yep. We use the second equation to solve for z, so plug it into the first equation. If you take it and plug it into the second equation, you'll always get 0 equals 0 eventually. When I go plug it into the other one, we'll distribute our -2 through. We distribute the -2 through, we've got 5y minus 8y. That gives us -3y. -2 times the -5 gives us a +10 equals -2. Subtract your 10 over. You get -3y equals -12. Divide by your -3, and you get 4 for your y. Now that we figured out what y is, can we figure out z? Work our way back up. Right? We can figure out what z is using this equation back up here again. Oops. Actually plug in the 4. So you get 4 times 4 minus 5 gives us 11 for that one. Finally, now that we have y and z, can we figure out what x is? Yeah, we can go all the way back up to that original equation that we solved for x. Our x will be 3 times 4 minus 2 times 11 plus 1. 12 minus 22 is -10 plus 1 is a -9. And then just like what we did when we had 2 equations and 2 unknowns, we'll write this as an ordered triple. So when you get an ordered pair, we had x comma y, right? This is what we refer to as an ordered triple. We'll write x comma y comma z, and then we'll have -9 for 11 for our final answer. And notice we get exactly one solution in this case. What questions do you have on that one? This takes a little while to get there, doesn't it? Okay. All right. So let's see if we can look at maybe an alternative way to help us solve the systems of equations. We're building up to something that we'll talk about in the next section. Let's see if we can think of an alternative way maybe to solve these systems so that we do not have to do all that substitution stuff. Maybe we can do some stuff that looks like elimination. Now notice in the previous problem, I could have rewritten my system in this way after I made my substitutions, because certainly once I got what the value was for z, I used that value for z to get the value for y. And then when I got the values for y and z, I went back up and got the values for x, right? So this is kind of an example of a system where you've already put in the work to figure out one of the values. And then you're going to do what you call back substitution to figure out the other values, which is exactly what we did. So we refer to this as a triangular system. Notice that we refer to it as a triangular system because you can kind of see this triangle going down here, if you will. All right? See that triangle here? Okay? So notice the first equation has an x. The second and third equations don't have an x. First two have a y. The last one doesn't have a y. So that's kind of that hallmark of a triangular system. Okay? All right, but notice what's helpful about triangular systems. Notice that last equation literally says z equals -2. So you know what the z is, right? We agree? Okay? If I know what z is, can I figure out y? Yeah, going back up, right? From here, I can plug in the z. and get y equals 3, it looks like. Because the 2 times the negative 2 would give you negative 4 and then add it to the other side. Now that I know the z and the y, can I figure out the x? Yeah, because again, I'm just going to go back another step, right? So you'd have x minus 3 plus negative 2 equals negative 3. Minus 3 minus 2 is negative 5. Add it, you'll get x equals 2. And so you'll have x, y, z equals 2, 3, negative 2. All right. So notice that when we have this triangular system, it's pretty quick to be able to go back and find your solution. Okay? So this is what our goal is, basically, to get to later on. Is that we want to try to rewrite our system of equations as a triangular system. Okay? Because once we have it as a triangular system, we know what the value to the last variable has to be, and then we just back substitute up to get the rest of them. Okay? So this is basically our goal for solving these things, if we can get it into that form. Okay. All right, so how do we get it into that form? Well, we're going to have a system of operations that's going to allow us to do this. And we'll have a special name for that later when we start simplifying our process and just keep track of coefficients rather than having to write the variables down each time. So we call two systems of equations are equivalent if the two systems have exactly the same solutions. And basically, this is already what we've been doing. We've been trying to rewrite the system that we're given into an equivalent system where we can figure out what the answers are, either through substitution or through elimination. That's what we've been doing. Okay? We're going to switch our focus over to elimination so that we can talk about being very systematic about putting our system of linear equations into an equivalent triangular system. Okay? Because again, we all recognize that getting our system into a triangular form, we can read the answers off pretty quickly, right? We agree with that? Okay, so that's our goal. All right, so what can we do? Well, there's 3 operations, and there are only 3 operations that we do in order to convert a system of equations into an equivalent one for what we refer to as elimination. Okay? Do not try to invent new operations. Okay? Oh, stick to these 3. All right? All right, the first one is we can multiply an equation by a non-zero constant. Okay? We've seen doing that already. We've done that, right? When we've done elimination, we've multiplied by a non-zero constant on both sides to try to get those coefficients to match up to cancel out. Okay? So this is one of our operations that we can do to try to convert a system of equations into an equivalent triangular one. Another one. Oh, by the way, why would we want to use a non-zero constant? Well, if we multiplied by 0, what would both sides of the equation end up being if you multiply by 0? 0 equals 0, right? They'd both be the same expression on both sides. It would be 0. In particular, if you multiply by 0, I always get a true statement, but I might have started with a false one, right? So multiplying by 0 is a bad thing to do, okay? So we don't want to multiply by things that are not that are 0. We want to multiply things by that are non-zero so they stay equivalent, okay? Another one, we can swap 2 equations. That's not going to change the system, the solution, right? All I did was just say write the equations in opposite order. Remember again that our goal is to try to get these, this system into triangular form. So I want to see that nice x in the upper left-hand corner, then a y, then a z, right? Well, maybe the first equation doesn't have an x in it, and the second one does. So you would swap the two rows so that you have an x in the upper left-hand corner. That's not going to change the number of solutions we have. The third one looks a little tricky. It's basically combining a couple of things. We can multiply one equation by a non-zero constant. Add that equation to a second equation, and then replace the second equation. Sounds complicated, but we've already done it, right? We've done it in stages. This just says do it all at once. Remember when we did elimination? We multiplied one of the equations by a constant to get those coefficients to match up, and then we added to get to make the variable go away when we did elimination, right? This is just writing it out in words. In the next section, we're going to call these elementary row operations. So I'll probably slip and call them elementary row operations as we're finishing off this section, even though we're not talking about rows, we're talking about equations. Okay. But these are going to be the three elementary row operations that we're going to talk about later on. Okay. All right, so let's put this to work. We want to solve this by elimination. So we've got the equations x plus 2y equals -1, y plus 3z equals 7, and 2x plus 5z equals 21. All right, so our first goal, again, is that we want to try to get this into a triangular system. Once I get it into a triangular system, then I can figure out what the equations are. So let's talk about what the steps are to get this in a triangular system. Okay? The first step, and this one there's not really anything going on with that, but the first step is that I want to see a 1x up in the upper left-hand corner. If I have a coefficient of a 1 on my variable, it makes it a lot easier to solve for it, doesn't it? So step 1 is that I want to see, get a 1x in the upper left-hand corner. Now notice I left out gaps here for where the variables are missing. This is just to help me line up things so that when I do my elimination, I can see where I'm basically adding down the columns. So that's the only reason why I spread it out. All right. Do I need to do anything to this system to get a 1x up in the upper left-hand corner? No. Okay, so step 1 is done, right? Step 2, use that third operation above. So that operation 3, the one that I'm talking about right here, to get rid of all the other x's. That's step 2. All right. What I mean by that is, up here I've got a 1x up in the upper left-hand corner. I want to get rid of the x in the second equation, and I want to get rid of the x in the third equation. Is there any x to get rid of in the second equation? No. So I need to get rid of the one in the third equation, right? So what do I want to do to get rid of this 2x. What do I need to do? Well, I need to multiply this x by -2 and add, right? Okay. So here's how we're going to write that. I'm going to, since I'm writing my steps over here. I'll do it this way. Put it off to the side. I'm going to put an arrow, and I'm going to write this as -2e1 plus e2 and replace, or not plus e2, plus e3 and replace e3. Okay. I'm going to take -2 and multiply it by equation 1. I'm going to add it to equation 3 and replace equation 3. Now, in this step, the only thing that's getting changed is equation 3. Okay? Equation 1 is going to stay the same. Equation 2 will stay the same. I'm going to do my multiplication and then add down all in one step. So -2 times x is -2, plus 2x gives me 0, right? -2 times y, 2y is -4y. Added to 0, we get -4y. -2 times 0 plus 5z gives me a plus 5z. -2 times -1 is 2, plus 21 gives me 23. Let me go through it again. I'm doing this as an intermediate step, but I'm not actually changing the equation, okay? -2 times x is -2x, plus 2x gave me 0. Okay? -2 times 2y is -4y, plus 0 is -4y. -2 times 0 is 0, plus 5z is 5z. -2 times -1 is positive 2, plus 21 gives me 23. Okay? So now notice I've got that x in the upper left-hand corner and nothing below it. To put this in triangular form, I'm going to work off of this y. All right? So step 3, we want to get a 1y in the second equation. Do I need to do anything to get a 1y in the second equation? Nope. So the fourth is use the third operation again. And I know we're almost out of time, which is why I'm hurrying a little bit. To get rid of the y's below. I don't need to, since I'm going to do that back substitution idea, I don't need to worry about the y above it. I just need to use the y below it. What do I need to multiply this y by to get rid of this -4y? 4, right? So we'll take 4 times equation 2, added to equation 3, replace equation 3. Again, the only equation that's going to get changed at this step is which one? The third one, right? 4 times y minus 4y is 0. 4 times 3z is 12z, plus 5z gives me 17z. 4 times 7 is 28, plus 23 is 51. It's almost triangular. Triangular technically has a coefficient of 1 on all your coefficients going down that diagonal. What do I need to do to both sides of that third equation to get a 1z? Divide by 17. Once you divide by 17, you've solved for z, right? When you solve for z, can you figure out y? Yep, and once you figure out z and y, can you figure out x? Yeah, so that's the process here, okay? So this is putting it into triangular form, so we get that last solution and then work our way back up to figure out the other two. Does that make sense? Okay. We're going to do more of these next time. You've probably noticed that the only thing that we're really keeping track of is the coefficients. The y, the x, the y, the z don't change. So we'll also start talking about how we can keep track of that and not have to write down the x, y, and z every single time. All right? Have a good weekend, everybody. We'll see you on Monday.